We were doing the numerical. I have this one. Percentage increase, right?
Yes, sir.
Isn't it? Percentage increase
Yes, sir.
in linear momentum. Okay. The linear momentum of a body increased by 20%. What will be the percentage increase in kinetic energy? Isn't it?
Yes, sir.
Yes, sir.
Oh. Let's continue now. Mir Mustaq, you got this one, right? Okay.
Yes, sir.
Coding permission. Okay, fine. Now look. Now percentage increase. This is the formula always. Percentage increase. Percentage increase in linear kinetic energy. Percentage increase in kinetic energy. That's the question, right? Check question once again. If the linear momentum of a body increases by 20%, what will be the percentage increase in kinetic energy?
Yes, sir.
Percentage increase in kinetic energy means change in kinetic energy. What is the change in kinetic energy? Final kinetic energy minus initial kinetic energy divided by initial kinetic energy into 100. This is the percentage increase in kinetic energy. Okay, now we need formula, kinetic energy formula EK is equal to E squared by 2m. Now, this is initial kinetic energy, EKI. Now, final kinetic energy after change in linear momentum, that is 20%. P plus 20% of P whole squared. There's a change we made, right? The linear momentum of a body increases by 20%. That means initially it was P. Initially it was P. Now 20% there is an increase in P divided by 2m. Isn't it? Now EKF is equal to P plus 20% means 20 by 100 of P whole squared divided by 2m. Then EKF final is equal to here P plus 0.2p, right? 0.2p whole squared by 2m. EKF is equal to 1.2p whole squared, isn't it? Whole squared divided by 2m. Or this is 1.2 is how much will come? 12 into 12? 1.44, right?
Yes.
1.44. 1.2 whole squared is 1.44 p squared by 2m. Okay, so this is 1.44 into p. This is EKI, initial kinetic energy. 1.44 times EKI. Any doubt?
No, sir.
Now substitute.
So what is
in this
P
equation.
here?
P linear momentum. Now substitute here. Percentage increase in kinetic energy is substitute. In final kinetic energy is 1.44. 1.44 EKI. This is a final kinetic energy minus EKI, initial kinetic energy, divided by initial one into 100. So here EKI we can take outside. It will come 0.44 into 100. That will be 44%. Is it clear?
Yes, sir.
Finish it. Yesterday, the question I gave is correct, right? Percentage change in kinetic energy, right? Was the question I gave correctly yesterday?
Yes, sir.
Yes.
Before this, have you done one numerical?
Yes.
Can you read the question I gave you yesterday?
Yes, sir. Sir, one question you gave was a heavy and light body have the same linear momentum. Who has more kinetic energy?
For yesterday, now I gave a question. I gave an answer, right? Read the question of this answer I gave you.
The momentum of body increases by 20%. What is the percentage increase in
Okay.
kinetic
So
energy?
did I give one problem like this? Is the kinetic energy of the body increased by 300%?
No,
We
no,
know
sir.
that. Oh,
No,
okay.
sir,
Just
you
finish
didn't.
now. Finish now. So this is 44%.
Sir, actually it is 1.44 into 100, right? In the last step.
Yeah.
It should be one.
No, 1.44 minus C. You didn't understand that stuff. 1.44 EK initial kinetic energy minus initial kinetic energy, isn't it?
Yes,
So
sir.
this is 1.44 EKI minus 1 EKI.
Okay,
So
sir.
difference is 0.44 EKI
Okay.
divided by, there is another EKI here, right? Into 100.
Yes, sir.
Now 44%.
Actually,
Did you
I thought
understand?
yes, sir. I thought that you took common EKI as common.
Is it over?
Yes, sir.
Next question. Very important question, this one. The kinetic energy of a body increases by 300%. Kinetic energy of a body increases by 300%. 300%. By what percentage will the linear momentum change? By what percentage will the linear momentum change? Look here, again formula. Percentage change in linear momentum. Same way, final momentum minus initial momentum means change in momentum divided by initial momentum into 100. This is a formula. Okay, so we need formula again. Kinetic energy is equal to, what's the formula here? P squared by 2m. Then P squared is equal to 2m EK. P is equal to root of 2m EK. This is the formula because we need linear momentum. Now changes this initial linear momentum. Final linear momentum after change is 2m. Okay. Question. Kinetic energy of a body increased by 300%. That means initial kinetic energy is EK. 300% it increasing means 3 times it's increasing, right? That's the meaning of it. Isn't it?
Yes.
Yes, sir. Yes, sir.
Say for example, a cost of an object is 100. Okay. Now 100% free means you have to get it free. You don't have to pay anything, isn't it?
Yes, sir.
Yes, sir.
Next week, it cost will increase 100%, means that cost will become 200. Like that, okay? So 100% means complete. So EK is the initial kinetic energy. 300% is increasing, means that value become plus 3K. So final kinetic energy now become 4 EK, isn't it?
Yes, sir.
Yes, sir.
So here they are saying the kinetic energy of a body increased by 300%. So initially 2 MEK, now the kinetic energy is 4 EK. Change, then momentum changed. Okay. So PF is equal to root of 2 MEK. This 4, root 4 I'm taking outside. So 2. So PF is equal to 2 into root of initial 2 into root of 2 MEK, right? 2 MEK what? Initial kinetic energy. PI, isn't it?
PI.
PI. Substitute now. Percentage change in linear momentum. Percentage change in linear momentum is equal to PF is how much?
So how
2
to PI?
Huh?
How to PI you got PF?
This is 2, right? Into
Yes, sir.
root of 2 MEK. This one PI.
Right, sir.
Okay. Yeah. So percentage change in linear momentum is 2 pi minus pi divided pi into 100. 2 pi minus pi is 1 pi divided by pi into 100. That means 100%. Okay. Pi will cancel out here, right? So 100%.
Yes, sir.
So what is the sentence to the right? Percentage of
Percentage change in linear momentum. Next heading, collisions. Collisions. Collisions, okay? Right on. Collision means interaction of two bodies. When two bodies come closer due to repulsion, they may go different directions. For example, here alpha particle experiment, Rutherford alpha particle experiment is there. In that, this is a golden nucleus. To this gold nucleus, we are projecting another alpha particle. That's also positive. When it is projecting here, it will get repelled like this. This is a collision. Or a car and truck colliding each other. Air molecules are continuously colliding each other. All these are examples of collision. That means collision between interaction between two bodies, so that state of motion is changed. Okay, right now. Collision is the interaction between two particles. Collision is the interaction between two particles by which its state of motion is changed. By which its state of motion is changed. By which its state of motion is changed. Next, two types of collision are Two types of collision are elastic collision and inelastic collision. Elastic collision and inelastic collision. Elastic collision and inelastic collision. Now let us see what is the meaning of elastic collision. Look, a glass of water, if you're taking, there are large number of molecules in it. They keep on colliding. If you keep the glass very close to your ear, do you hear any sound?
Yes, sir.
Do you hear any sound? A glass of water keeping
No,
near
sir.
your
No,
ear?
sir. No, sir.
No. That means during this collision, they are not producing any sound energy. Or if you keep a glass of water, will it be automatically heated?
No, sir.
No, sir.
No, because there is no heat energy liberated during this collision. So in this collision, no energy loss is taking place. So here very closely, if you observe, these molecules, when they come closer, while they are making random motion, these molecules are continuously moving. They are not having any physical contact. They come very closer to it. And the higher class, I think chemistry will study electron clouds will overlap and they will push it apart. So that without touching itself, they will go away if they come closer. So molecules, when they come very closer, suddenly they will be repelled away. So the contact time is negligibly small. These kind of collision, there is no energy loss. That means kinetic energy is conserved. No energy loss. And linear momentum is always conserved. These kind of collision are known as elastic collision. It's mainly air molecule, gas molecule, these kind of things, elastic collision happen. There you can see collision time is negligibly small. But another case, a car colliding with a truck, you can hear large amount of sound
Yes, sir.
and heat. And that speed of the car and truck completely changing.
Yes, sir.
So total kinetic energy before collision and total kinetic energy after collision is different. So there you can see energy is lost. That's why that sound is heard or heat is generated. But linear momentum is conserved there also. Total linear momentum before collision is equal to total linear momentum after collision. These kind of collisions are known as non-elastic collision, non-elastic or inelastic. In case if car and truck colliding, suppose if they get stuck together and moving together, that means contact time become infinity. This kind of collision we can say perfectly elastic. Or some clay throwing onto the wall gets stuck. That is almost similar to inelastic collision. Or non-elastic collision or inelastic collision, we can say contact time is infinity. In elastic collision, contact time is negligibly small. So this is an easy way we can identify them. Is it clear?
Yes,
Yes,
sir.
So
Right.
the example you gave that the car and truck moving together after collision. So,
After collision, if they get stuck together, say for example, they got hooked together and they move together. Sometimes they pull along with it, isn't it?
yes, sir.
So,
So
for example,
that
a car get trapped with a truck. So truck also will take this car along with it.
Yes, sir.
That means common velocity will attain that time.
So, sir, is that perfectly inelastic?
See, actually 100% elastic and 100% inelastic are not easy to find. But only one example of perfect elastic collision is molecules. Water molecules, water molecules, air molecules, etc.
Yes, sir. But
Perfectly
that
inelastic means mud thrown to the wall, gets stuck. That permanently stuck there.
yes, sir.
Sir, but
Like that.
no voice is heard here.
No?
Voice is heard like in truck and car accident. When you throw mud to a wall, no voice or noise is heard.
No.
It will just go
You
and stuck it.
just take mud onto the wall. Click, one sound will hear. There will be sound.
That small sound only.
That's enough because
Okay.
that energy you are throwing there to get you don't have to stick clay or mud onto the wall. You don't have to exert much force,
Yes, sir.
isn't it? You take a big stone and throw it. You can hear tuck, one sound you'll hear because there you are exerting
Yes, sir,
more
yes.
energy to throw it.
I got
Isn't
it.
it?
Yes,
Yeah,
sir.
right. And heat will generate slightly. Right. So first one, elastic collision. Elastic collision. Elastic collision. So have you written the definition for collision?
Yes, sir.
Yes, sir.
Yeah. Now elastic collision. It is a collision in which. It is a collision in which. It is a collision in which both. It is a collision in which both linear momentum and kinetic energy are conserved. It is a collision in which both linear momentum and kinetic energy are conserved. It is a collision in which both linear momentum and kinetic energy are conserved. Example, collision between air molecule, water molecule, etc. Collision between air molecule, water molecule, etc. And in elastic collision, or during elastic collision, the time of contact is negligibly small. Next heading, non-elastic collision. Non-elastic collision. Non-elastic collision or inelastic collision. In non-elastic collision, or inelastic collision, linear momentum is conserved. Linear momentum is conserved. Linear momentum is conserved. But kinetic energy is not conserved. Example, collision between the truck and a car. For perfect non-elastic collision, contact time is infinity. Next heading, velocities.
Sir, please can you say the last point, sir?
What is that?
Say the last point, sir, for
perfect inelastic collision or non-elastic collision, contact time is infinity. Next heading, expression for velocities of objects, expression for velocities of object after elastic collision. After elastic collision. Expression for velocities of object after elastic collision. Look here. after one-dimensional elastic collision, okay? One-dimensional elastic collision. There are two types, one-dimensional and two-dimensional. One-dimensional means suppose this is an object. This is the line passing through the axis. Another object come and hit exactly here. Head-on collision. It's called head-on. That means after hitting also, they travel along straight line. In this case, this object come and hit on this side. So this goes this way, this comes this way. This is two-dimensional elastic collision. First we are studying about one-dimensional elastic collision. Okay, look here. Draw the diagram. This is an object, mass m1, initial velocity u1. Colliding another object, m2. And initial velocity u2. After their collision, their action and reaction will come, their velocities are changed. Draw this diagram, okay? Now this become m1 v1. And this become m2 v2. Moving like this. Okay. So this is object A, this is object B. Object A, object B, object A, object B.
So what does arrow mark represent?
Velocity. It's moving in that directions.
So what do the diagrams in between represent? The two diagrams in the middle?
Colliding each other. Same thing we studied in Newton's third law of linear conservation of momentum, right?
Yes, sir.
Write down. Very clearly, I'm telling you, write down the notes perfectly and revise regularly. Now we have no option to monitor you. And don't expect like in 10th standard, anybody will be after you. When the exam come, I will open. In 3 hours, I will study and learn good marks. It's impossible in 11th standard. You need update learning. That means from the beginning, again, it is repeating. And final exam also, the whole book is coming. Remember that. So you need thorough revision. We are all speaking it very continuously because 30 years I'm teaching the same thing. That's the main reason. And daily 3 times I'm teaching. 1 in school, 2 tuition batches. That's what we can recall. Even we make mistakes. You are hearing it only 1 time. So revision is very, very important. I'm telling you many times. Because here class attendance also out of 80, usually it comes, see, what is the class? M1 and M2. Traveling with initial velocities. Traveling with initial velocities u1 and u2 respectively. Let us consider 2 bodies of masses m1 and m2 traveling with initial velocities u1 and u2 respectively. After one-dimensional elastic collision, the final velocities are after one-dimensional elastic collision, the final velocities are v1 and v2 respectively. v1 and v2 respectively. Now you write. For elastic collision, write along with me, otherwise you won't have time. For elastic collision, kinetic energy is conserved. For elastic collision, kinetic energy is conserved. For elastic collision, kinetic energy is conserved. Now write half m1. What is the law of conservation of kinetic energy? Total energy
V
before
square
collision
half
is equal to so half m1 u1 squared, kinetic energy of this body, plus half m2 u2 squared, total kinetic energy before collision, is equal to half m1 v1 squared plus half m2 v2 squared. Here half will cancel out. You see, half, all this half will cancel out. And here we can write m1 u1 squared minus m1 v1 squared. This one I'm bringing here. Is equal to m2 v2 squared minus m2 u2 squared. Okay. Here m1 we can take outside. u1 squared minus v1 squared is equal to m2 into v2 squared minus u2 squared. This is equation number 1. Is that over?
Yes, sir.
Yes, sir.
For elastic collision, linear momentum is conserved. Linear momentum is conserved. That means total linear momentum before collision, m1 u1 plus m2 u2, is equal to m1 v1 plus m2 v2. m1 u1 minus m1 v1 is equal to m2 v2 minus m2 u2. Then m1 into u1 minus v1 is equal to m2 into v2 minus u2. This is equation number 2. This is equation number 3. This equation we need two equation, we need a substitution again. Now dividing 1 by 2. 1 by 2. When you are dividing, see 1 by 2. m1 cancel. Then u1 squared minus v1 squared divided by u1 minus v1 is equal to v2 squared minus u2 squared divided by v2 minus u2. m2 u2 AB, that's colliding each other. Then now look here, for elastic collision, kinetic energy is conserved. Then we can write here half m1 squared plus half, mute your mic please, m2 u2 squared is equal to half m1 v1 squared plus half m2 v2 squared. So here half m1 v1 squared. Please mute your mic. u1 squared minus half m1 v1 squared is equal to half m2 v2 squared minus half m2 u2 squared, right? Half m1 u1 squared minus half m1 v1 squared is equal to half m2 v2 squared minus m2 u2 squared. So here half will cancel out. Half cancel. Then we get m1 u1 squared minus m1 v1 squared is equal to m2 v2 squared minus m2 u2 squared. Now here, we brought to left side, right? Okay. Now here m1 we can take outside, u squared minus v, u1 squared minus v1 squared is equal to m2 into v2 squared minus u2 squared. This is equation number 1. Was it correct? Is it correct which I gave you before?
Yes, sir.
Yes, sir.
Next,
Yes.
by law of conservation of linear momentum. M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. Then M1 U1 minus M1 V1 is equal to M2 V2 minus M2 U2. Now here M1 we can take outside. U1 minus V1 is equal to M2 into V2 minus U2. This equation number 2, this equation number 3. Okay. Now dividing 1 by 3. Equation 1 by 3. We are dividing it. When dividing, see M1 we can. Then
Sir, why did we
U1
take
squared
that question
minus
number,
V1 squared
equation
divided
number 2?
by U1 minus V1.
Sir, why did we Sir, why did we take that question, equation number 2, sir?
This one, I'll show you what is the reason I'll tell you. I need that equation again later.
Okay, sir.
U1 minus V1 is equal to here V2 squared minus U2 squared divided by V2 minus U2. This is A squared minus B squared. That means A plus B, A minus B. So U1 plus V1 into U1 minus V1 divided by U1 minus V1 is equal to V2 plus U2 into V2 minus U2 divided by V2 minus U2. Now this U1 minus V1 cancel, U1 minus V1 cancel, V2 minus U2 this cancel. Then U1 plus V1 is equal to V2 plus U2. This is equation number 4. Have you finished up to here?
Yes, sir.
Now I am removing this part, okay? This one I am removing from. Now look, from here, first we will get V1 because we need formula after collision. So first let us take it. V1 is equal to V2 plus U2 minus U1. This is question number 5. Any doubt?
No, sir. No, sir.
No, sir. No, sir.
Question it is from 1 and 2, right?
From equation 4. From equation 4, I kept V1 here. U1 I brought to this side. That's all.
Okay, sir.
Okay. Any doubt?
Yes, sir. No, sir.
No, sir. No, sir.
Now this V1 value substitute in equation number 2. That's what I kept equation number 2 there. Okay. Substituting a value of V1 in equation number 2. Now here write it. Okay. M1 U1 plus M2 U2 is equal to M1. This is V1. V2 plus U2 minus U1 plus, okay, plus U2 minus U1. U2 minus U1. Okay. M1 VU1 plus M2 U2 is equal to M1. Instead of V1, V2 plus U2 minus U1. Then, oh, sorry.
Sir, M2V.
M2 V2, right?
Yes, sir.
M2V2. M2 V2. We have substitute. Now open the bracket. M1 U1 plus M2 U2 is equal to M1 V2 plus M1 U2 minus M1 U1 plus M2 V2. We need V2 now. So keep V2 on the right side, bring all of it to the left side. Okay. So we can write M1 U1 plus M2 U2, this plus M1 U1 minus M1 U2 is equal to M1 V2 plus M2 V2. So here now left side we can write M1 U1 plus M1 U1 2 M1 U1 plus M2 U2 M1 U2. That means M2 minus M1 into U2. U2 common is equal to, this will be M1 plus M2 into V2. We need V2. After collision, what is the velocity? Then V2 is equal to M2 minus M1 into U2 plus 2 M1 U1 divided by M1 plus M2. Or finally we can write V2 is equal to M2 minus M1 into U2 plus 2 M1 U1 divided by M1 plus M2, M1 plus M2, because this is common to both. So this is the way this equation is usually represented. V2 is equal to M2 minus M1 by M1 plus M2 into U2 plus 2 M1 U1 by M1 plus M2.
Sir, so this is the final equation for velocities of elastic.
Now we need V1.
Okay.
Similar way we have to substitute for V1.
Sir, but V1 we have, right? V2 plus U2 minus U1.
So V1 when you are calculating, it will come M1 minus M2 divided by M1 plus M2 into U1 plus 2 M2 U2 by M1 plus M2. It will come like that. Now again from equation 4. Again from equation 4. There is M1, right? There is M1 here. Again from equation 4. Here we got V1. Now we have to get V2. V2 is equal to what is V2? U1 plus V1 minus U2, isn't it? This equation number. How much? This is 6. This is 7, right? Isn't it?
Yes,
Yes,
sir.
sir.
Now substituting 7 in equation 2 again. That means here we have to substitute. M1 U1 plus M2 U2 is equal to M1 V1 plus M2. What is V2? U1 plus V1 minus U2. Substitute here. M1 U1 plus M2 U2 is equal to M1 V1 plus M2 U1 plus M2 V1 minus M2 U2. m1u1 plus m2u2 is equal to, now v1 keep there, okay? V1 terms keep there. Plus, and this is minus m2u1 plus m2u2 is equal to m1v1 plus m2v1. That v1 term I kept on the right side. Now here, m1u1 minus m2u1. So m2u2, m2u2, 2m2u2 plus m1, take common, u1, m1 minus m2, m1 minus m2.
Sir, no, m2 into u2 minus u1, right?
Wait, I'll come to that point. Okay. m2u2, m2 into 2m2u2, m1 minus m2 into u1. Okay, is equal to, this is m1 plus m2 into v1. Now v1 is equal to m1 minus m2 into u1 divided by m1 plus m2 plus 2m2u2 divided by m1 plus m2. So same like this. This is equation number 9, 8, 8.
Sir, if we substituted 6 in 5, number 6 in 5, we would have gotten the same answer, right?
Have you finished this?
Yes, sir.
No, sir. You do have.
Okay. Now here we have to go for special cases, okay? Special cases. Look, we have this formula V1 and V2. You should know it by heart. Look here. Suppose there are two objects. This is M2. Another one, small one is M1. First one is M1. Usually, which we are throwing, which we are going, that we call projectile. Where it is hitting, that we call target, usually, okay? So initially, we can say condition. M1 is equal to M2. Both the bodies are having same, okay? What will be the velocities after elastic one-dimensional collision? That's a question. So when M1 is equal to M2, Substitute in the equation of V1. Two bodies, same mass, M1 U1, M2 U2. After collision, M1 V1, M2 U2. Question: if they make an elastic collision, their masses are same. What will be the velocities after collision? M1 is equal to M2, right? If M1 is equal to M2 is equal to M, then what will be the velocities V1 and V2? Substitute here. First case, M1 minus M2, right? Take V1. In V1, when you are taking M1 minus M2, so this term becomes 0. First term, okay? Then here 2 M into U2 divided by 2M. This cancel. So V1 become U2, right?
Yes.
And this U2 will transfer to this body. Suppose this is 5 meter per second. This is 10 meter per second after collision. This will gain 10 meter per second. And same way, substitute here. We can say that will come V2 is equal to U1. This will become U1. Substitute and check. That means their velocities are exchanged. It means in a glass of water, molecules are all identical size. Suppose a numerical they are asking, if they are colliding each other, one molecule traveling with 10 meter per second, another 5 meter per second after collision, what will be their velocities?
They will exchange.
They will exchange. First molecule have 5, second molecule have 10. Like that. You can see while playing carom board, approximately you will get this idea. See, one coin is at rest. Okay? And this is striker. If it exactly here, you can see this will fly off and this will almost come to rest. Like that. Not exactly perfectly example, but usual experience we see that. You understood this part?
Yes, sir.
So your example problem I told you, 2 molecules they will give you. So you should know molecules are of identical size in kinetic theory. We are studying. So their velocities are exchanged right now. In this case, velocities are exchanged between them. Velocities are exchanged. Note that. Next question. M1, M2, M1 is very, very smaller than M2.
The question.
M1 we can take a 0.
So it's a question.
Next. M1 is very, very smaller than M2. And M2 is at rest. This is U1, this is U2. M2 at rest. Right. Special case after. M1 is very, very smaller than M2. And M2 at rest. Find out velocities after collision. First equation, let us see. M1 is very, very smaller than M2. So here, this M1 cancel, this M1 0. M1 0, M1 0. So what is remaining now? M2. That become 1. So V1 become U1.
How, sir?
Wait. M1 cancel. M1 0, M1 0. M2, M2 cancel minus U1 will.
Minus U1.
Isn't it?
Yes.
And here
Yes,
U2 0.
U2.
So the whole thing will be 0. U2 0, right? Target at rest.
Yes, sir. Yes.
Second case, V2. How the V2 will come? See, V2, M1 0. This is 0. This is 0. So M2 cancel. That become U2, right?
Yes, sir.
Sorry, U2 0. U2 0. So this term becomes 0. U2 0, right? So this term becomes 0.
M2 M1 U1 by M1.
This one you take, how much will come?
2 M1 by
U1 by
M1.
0. M1
Sir,
0.
M1 is 0.
So that becomes 0 itself,
0.
right? Completely.
Yes, sir.
What does it mean?
The state of rest of the other one is transferred here.
No. Second body is at rest.
Okay,
That
so
remain
V2
at
remains
rest.
in rest.
First
That
body
remain at
will
rest.
bounce back.
bounce back with the same velocity. Can you tell me one example?
Throwing a ball to a
On a
Yeah,
wall.
throwing an elastic ball. Not exact example, throwing an elastic ball onto the ground. Earth is a huge body. Earth is very big, right? Huge body. And you are throwing a ball onto it. So Earth will not go away after you throwing. It will remain same. But this will bounce with the same velocity. But since it's not perfectly elastic, some energy will be lost. So bouncing won't be same height you have thrown. Okay?
Okay, sir.
Sir, how V2 becomes 0?
U2 0. So whole thing
Yes, sir.
0. M1 is 0.
How is the M1 0?
M1 is very, very smaller than M2.
Ah,
Okay? Next case.
yes.
Yeah. Next case. M2 is very, very smaller than M1. And U2 is equal to 0. Then tell me what happens.
V2
That means M2 is very, very small, negligible and at rest. A huge body come and hit here on this. This is M2 and it is in 0. This is M1 coming with U1 and hitting here. Then what happens? That means Earth while
Sir,
moving
here M2 is
is
at
hitting on a
rest.
small body. Huh?
Here M2 is at rest.
M2 at rest. Target at rest. Tell me. You will see first body, heavy body will go without any change. So V1
Yes,
is equal to U1. But second
U1.
body, V2 is equal to 2 times its velocity will come. 2 times U1 will come. Velocity will be doubled for the second body. You can check it. Here M2 take as 0. M2 neglected. M2 0, U2 0. So these are the special cases. Finished?
Yes, sir.
Next one, coefficient of restitution. Coefficient of restitution. Look, here one body, there is another body. Traveling with a velocity, there is M1, U1, M2, U2. So their relative velocity, we can write U1 minus U2, modulus you take. Okay? After collision, their velocities become M1 become V1, M2 become V2. Their modulus is say V1 minus V2. Modulus, only value we need. Suppose this is 5, this is 10.
Sir, coefficient of what, sir?
Restitution. Okay. Now relative velocity. V1 minus V2 divided by U1 minus U2. This ratio is known as coefficient of restitution E. Okay, it means suppose this is traveling with 5 and 10. If they are same mass, this become 10, this become 5. Now difference in 10 minus 5 is 1. I mean 5, right? Down also that is 5. Modulus only I'm taking. Then answer is 1, right?
Yes, sir.
So if coefficient of restitution is 1, that means it is elastic collision. Elastic collision. Suppose after colliding some energy is lost. Now this become 3, this become 1. Then it will be, answer will be like this. V1 minus V2, that become 2. First become 5. Say it's less than 1. So if it's less than 1, there is energy loss. That means it is inelastic collision or non-elastic collision. Suppose you are throwing a cracker and it explodes. So velocities after explosion is more than velocities before. In that case, E is greater than 1. This is called Superelastic collision. Superelastic collision. 3 times. So coefficient of restitution is the ratio of relative velocity of the two bodies, after collision to relative velocity of the two bodies before collision.
Sir, can you repeat?
The ratio of relative velocity of the two bodies after collision to relative velocity of the bodies before collision.
Sir, how did you get that 2/5, sir?
What?
You got that ratio as 2/5, right?
Just one example I have taken.
Okay, sir.
Elastic collision in 2 dimensions. Elastic collision in 2 dimensions. Look here. Draw the diagram. This is now target. This is the reference line along x-axis. Okay. This line also x-axis. So target is along x-axis, or projectile also along x-axis. Through here it moves and come and hit at this corner. Then you know what happens, right? This will go this way. It will be thrown to this side. And this will come down here. This will go this way down. Okay, it will go to this side. M1, U1. M2, U2. This is M1, V1. Goes this way. This becomes M2, V2. It comes this side. From actual direction, this turned an angle. This is theta 2 because theta 1, M2 V2, that's 1. Similarly, this is from actual direction, it goes to here. That is theta 1. Now this velocities we can resolve into 2 components, isn't it?
Yes.
This component here, because momentum is a vector. So momentum can resolve into 2 components. So this will be M1 V1 sin theta 1. This side will be M1 V1
cos theta.
M1 V1 cos theta. Similarly, this one also we can divide. This one. And here this one. This is M2V2 cos theta 2. This will be M2V2 sin theta 2. This is the diagram. But kinetic energy, if you're marking, Kinetic energy half m1 v1 squared. This is half m2. Half m2 v2 squared. This is kinetic energy. Okay. Have you written?
Yes.
Have you finished the diagram?
Yes.
Yes,
Then
sir.
tell me. Oh. Now here in elastic collision, linear momentum is conserved, right? Linear momentum is conserved. In elastic collision, write down. In elastic collision, linear momentum is conserved. In elastic collision, linear momentum is conserved. Okay. But here linear momentum is a vector. Before collision, they have only x-axis. After collision, linear momentum is x and y-axis. So first we have to take along x-axis. Along x-axis. Okay. Look, before it will be m1u1. This is coming along x-axis. Plus m2u2. Both are in x-axis. That's equal to here. After collision, m1 v1 cos theta 1 plus m2 v2 cos theta 2. This along x-axis. Along y-axis, no linear momentum. So along y-axis, this becomes 0. And after collision, m1 v1 sine theta 1 minus downward m2 v2 sine theta, because they are opposite. Now kinetic energy is also conserved. Before collision, half m1 u1 squared plus half m2 u2 squared before collision. After collision, half m1 v1 squared plus half m2 v2 squared, because